So J, the Jacobian matrix, is the generalization of the derivative to the most general case of many inputs and many outputs. Let me make that comparison even clearer by filling in this table here. So here I'm going to do the one-dimensional case, and in the right column I'm going to do the general case. So here we have f of x, where x is a scalar and f is a scalar. And on the right we have f vector of x vector, which means that there are many variables because we have a vector as the input, and there are many outputs because our f is a vector. So in this analogy, we know that given a value of x, we find a value of f, right? That's what the function f of x means. But if we increase x by an amount dx, then we know that our function f will increase by an amount which is equal to the derivative of f with respect to x times dx, okay? And this is what we conventionally call df, okay? Which, if we were drawing it in the traditional way, so we have a certain function here. So remember, if this is a certain value x, and now we increase by an amount dx, so we end up here, yeah? And dx is small enough. This means that the function, we are zooming in enough that this function behaves like a straight line locally, yeah? So then x increased by an amount dx is equivalent to increasing f. So f is increased by an amount which is df. And df is equal to the derivative df over dx multiplied by dx, okay? So this is the one-dimensional case. Here, in the general case of many dimensions, we have a vector x vector, which means all of the different variables in the input written as a single vector x, and the output is a vector f, which means all of the different outputs of f of the function written as a single vector, okay? And now if we increase our inputs x by an amount dx, where now dx is a vector, the output is f plus the Jacobian matrix times dx, where this increase here is what we usually call df, the total differential of f. And in this case it is a vector, okay? So I hope that this comparison is very clear and that you notice that what was the derivative before now becomes the Jacobian. Even better is if we realize how all that we have learned about derivatives so far fits into this model of the Jacobian. So think about this. In the simplest case of a one-dimensional function going into f of x, yeah, so 1 to 1, we calculated the derivative of f with respect to x, such that df is simply this derivative df with respect to x, which is the slope of the tangent to the line multiplied by dx, okay? Now, when we had multiple outputs, we covered this in chapter of differentiating and integrating vectors, yeah? When we have multiple outputs, so the derivative of a vector with respect to its only variable, when we are going from 1 to m, we saw that we could actually define the differential of a vector, and the differential of a vector was written as the derivative of each of the components of the vector with respect to x multiplied by dx, okay? You remember we saw that. Then in this chapter we started looking at partial derivatives in a function that converts n input variables into one output, and you saw that the partial derivative of f with respect to each of the input variables, and you could define the total differential df as this equation: partial of f with respect to x1 times dx1 plus ... plus partial of f with respect to xn times dxn. And finally, now we have learned that the total differential in the general case of a function with n input variables and m component outputs, then the total differential of this vector f is the Jacobian matrix, which contains all of the partial derivatives of all of the outputs with respect to each of the inputs. So we create this grid, multiplied times this vector of the differentials of the input. Yeah. But now note, so this is the most general case, meaning that each of the previous cases was a particular case of the general case. For instance, take this second case here. We can actually write this sum of terms as a product between a vector, between this matrix, which has one single row but n columns, times the output dx vector. Okay, so we can rewrite this known expression for the total differential of f as a vector containing all of the partial derivatives, a row written in a row, times the vector of the differentials of the input written in a column. Okay, so this can be interpreted as the Jacobian matrix. So this is clearly the Jacobian matrix in the case when m equals 1. So this is just a special case of this. Okay, the same is true here. So this is a single column, but this can be seen as this matrix in the special case when n equals 1, when there is only one input, and therefore we have only one column. So this is what we saw. And finally, the one-dimensional case is also a Jacobian matrix in the special case that m equals 1 and n equals 1. So instead of going from n to m, we're going to 1 to 1. So this matrix is a 1 times 1 matrix, which contains the differential of f with respect to x. Okay? So I really like when this happens in maths. You start learning things, and things seem to be getting more and more and more complicated, and eventually when you learn the most general scenario, it turns out that you can forget about all of the above. It wasn't getting more complicated, it was actually getting simpler. So this is the simplest it can get. df equals j times dx. That's really simple. And each of the previous cases was simply a particular case of this, just with different number of n and different number of m. Okay? So that's what I'm writing here, that this is a Jacobian matrix with size 1 times n times the vector dx. This is a Jacobian matrix with size m times 1 times the scalar dx. And this is a Jacobian matrix of size 1 times 1 times vector times the scalar dx. Okay? So that is the Jacobian matrix. And it's the most general way to talk about derivatives for functions that have many inputs and many outputs. Okay, thank you very much for listening, and see you in the next video.